Good day, students. This is Mr. Reynolds, and today we are on our final topic of the first year of DP Physics, and that is further cosmology. We're going to sort of take a next step past the cosmology where we left it last week, and we're going to talk about topic D.5. D.5 is called Further Cosmology. This is an HL only topic, but it just goes into a little more detail about cosmology, and whether you're taking HL or SL physics, it's just some interesting things. So today we're going to talk about four main topics, and we're going to sort of jump through them fairly quickly. First, I want to talk sort of about the cosmological principle. Cosmological principle. Now, the cosmological principle is based on observations we've done of galaxies all over, looking in all different directions. And what the cosmological principle basically says is that there is no special part of the universe. If you remember back to last week, we talked about the Big Bang and how the Big Bang didn't happen at one place. Instead, the Big Bang happened everywhere. There's no preferred spot in space. You can't point to a certain place and say, oh, that place is sort of different than other places. When viewed on a large scale, we say that the universe is homogeneous, or some people say homogeneous. I don't know, whichever one you want. Homogeneous basically says on a large scale, all parts of universe are similar. Now, I say a large scale. I mean, obviously, you can look around your room right now, and you can tell that some parts of your room are different than others. Right now, in front of me, I've got a computer. Behind me, I don't. There's a difference. But we're talking on large scales. We're talking on billions and billions of galaxies. Everywhere we look, the galaxy seems to have sort of a pretty constant composition. The other thing we can say about the universe is that it is isotropic. Isotropic. Pretty much everywhere we look, we see basically the same thing. This is, let's imagine this is our universe, this big blobby thing. Let's imagine we were here on the left side. If we look to the left, we'd probably see darker area because, there just aren't a lot of stars out there. If you look to the right, well, it's going to be a little bit brighter. We'd see more galaxies. That's not what happens. From our observations, the universe is isotropic, which means everywhere we look, we see pretty much the same thing. Again, it's not all perfectly identical, but on a large scale, it's the same thing. And again, this all goes back to the cosmological principle. Cosmological principle says, in general, on a large scale, everything is pretty uniform in the universe. Everything's pretty universe. There's no giant gradient of density of stars or something like that. It's all pretty constant for all observers. If we went to another galaxy far away and looked all around from that galaxy, we'd see pretty much the same thing we see from here. Okay, so this is the cosmological principle. I know sometimes that we like to feel that our part of the universe is special over everybody else, and maybe it is. Maybe there is something special about that, but certainly that does not meet our observations thus far. Now, I do say things look the same in all directions, but when we do look in all directions, we talked about last week, we have this thing called the cosmic microwave background, and we'll sometimes call that CMB. In all directions, we see microwaves coming from all directions. They don't seem to be coming from something. They just seem to be coming from everywhere. As far as we can tell, that is energy that was given off in the Big Bang. And it has been traveling for 14 some odd billion years to get to us. It's just now gotten to us. Since the universe has expanded quite a bit in that time, those really small wavelengths, when they're initially created, have now stretched out and are now much bigger wavelengths of microwaves. It turns out that while the microwaves in all directions are pretty much the same, they're not exactly the same. Let me see. Maybe I don't have an image of this. They're pretty close. Thought I had an image, but I guess I don't. In all directions, the microwaves are sort of similar but not the same. What that tells us is that there are some fluctuations. Now, this is important. It's important that when the Big Bang happened, everything wasn't perfectly uniform. When the Big Bang happened, in whatever form the universe was in, when the Big Bang happened, it wasn't all totally uniform and nicely mixed together. If it was, and all energy, which later became matter, was perfectly distributed, then that energy and matter would have spread out, and our universe would be perfectly uniform and, constant. And it's not. We have areas of our universe that have things in them, like our planet. Our planet is an area that has a lot of matter gathered in one place. You go off our planet, and there are other areas where there's not a lot of stuff. There are some fluctuations in the cosmic microwave background, and what we have said here is that those fluctuations give structure to universe. It puts things in the universe. For example, if when the Big Bang happened, a couple of these little gas particles were sort of closer together, and again, there aren't gas particles Big Bang, but whatever, close enough. You get the idea. Well, those little particles may have attracted each other. And then they'll gather together. Now they've got a stronger gravitational force. So now they can attract other things and other things and other things. And all of a sudden you have a star. Where if the universe was perfectly uniform and even all the way through, well, you would never have molecules mixing together. They'd be equally pulled on all sides. And so cosmological principle says on a large scale, the universe is homogeneous and isotropic, but there are fluctuations. We've recognized that it's certainly not perfectly homogeneous and isotropic. If it was, the universe would be incredibly boring, and we certainly wouldn't be here as we currently are. So the fluctuations in the cosmic microwave background, they give structure to the universe. Areas of high density became stars, which became other things, planets, and whatever, became other stuff. So, cosmological principle and the fluctuations in the CMB, they definitely go together. Now I want to move on. I want to talk about two topics that people hear a lot about, but people often get wrong. People have some wrong understandings of these things, and I think they're pretty interesting. So I want to talk first about galaxies. Now, what we do, we can look at these galaxies, and let's just model a galaxy. A galaxy, of course, is a collection of stars. And so, in the galaxy, for the most part, you got your general area where most of the stars are in the galaxy. That's sort of your normal galaxy, okay? And again, it could have different shapes and whatever, but this is your general area. But in any galaxy, there are some stars sort of outside of the galaxy. They aren't really in with the rest of the stars. They're sort of off by itself. But, like all the other stars, they all orbit a single point. There's a single point in the center, and every star in that galaxy orbits that center point. Our star, our sun, orbits the center of our galaxy. Okay? Now, what scientists did is they wanted to understand what kind of motion should you see from a galaxy. So we looked at two areas. We looked in the core of the galaxy, and then we looked in the halo of the galaxy, the outer layers. Now, based on the math, and based on a lot of complicated calculations and stuff, what they said is, in the core of the galaxy, that the velocity was pretty much going to be proportional to the radius. Now, we actually have an equation, and certainly in class we would actually go over this equation, we would derive this equation, but because of sort of what we're doing now, we're not going to deal with that. But the equation, the data booklet says this. It says velocity equals the square root of 4 pi g rho over 3 multiplied by r. Now, what this says is, our 4 pi g rho and 3, those are all constants. All of these are constants, and so basically, as the velocity doubles, the radius doubles. So if I was going to draw a graph of rotational velocity versus radius, if we're talking about the core, we're going to draw a proportional graph. We're going to draw a graph that pretty much goes up from the origin, and it goes up to the right. And guess what? That's pretty much what we see. When we actually measure what's going on, we pretty much see the velocity is proportional to the radius. The interesting thing comes with these stars that are going around the outside. Because in the halo, those stars aren't acting like one object. You see, those stars are sort of separated from all the other stars. They don't have all the gravitational pull. And so what we can say with those stars is we can use our basic rotational motion stuff. We could say things like mv squared over r equals gmm over r squared. Okay, the centripetal force that's causing those stars to go in a circle is the force of gravity from the galaxy. Now, since these stars are on the outside of the galaxy, we just consider all the galaxy to have a center mass right in the center. Now, if you do your calculations, you move things around, you're going to see that v equals the square root of g, cancels m's, so big M, multiplied by 1 over r. Okay, square root of gm times 1 over r. I hope I didn't do anything wrong there. That looks pretty good. So what that tells us is the velocity is proportional to a 1 over r graph. So a 1 over r graph would be something like a 1 over x graph. It would be something like this. We would expect those stars on the outside of the galaxy to sort of, fade off in velocity the farther out they get. Just like Pluto is much slower than the orbit of Earth or Mercury or whatever. But that's not what we see. That's not what we see. When we actually measure the rotational velocity of those outer stars, we use the Doppler effect. We look at the light from the stars on the outside and do things like that. What we actually see is the velocity stays roughly constant. Now it can change a little bit, but roughly constant. I'll show you a better image. Not that my image is bad. This is a galaxy M33. Oh, we're all over the place here. So you can see here on M33, let me get a pen to write on here. So you basically have, here's sort of the core of the galaxy. And you see it starts to go up pretty much in proportional graph. And again, we would expect it to fall off as a 1 over x graph, but that's not what we see. We see that it even continues increasing a little bit, or stays pretty constant. It slows down the growth, but it does stay pretty constant. So what scientists did, whenever scientists see some observation that doesn't match what they expected, they're going to say, well, what would cause that? There's something we don't know about that causes this. And what they figured out, the thing that would cause this to happen is if there is a lot more mass in the... I think I've crashed notability. I'm doing a lot of that lately. Let's try this again. All right. What they said is there's a lot more mass in those outer layers than we think. We look at all the stars in the halo and we see a few things. But they're saying there's a lot more mass out there. There's extra mass that we can't detect. We call this stuff dark matter. Dark doesn't mean it's black. It's just that we can't detect it. Okay, it could be something that's black, sure, that would be tough for us to detect, certainly, but it could be a lot of things. And so scientists are trying to figure out what is that stuff out there that we can't detect. There are two sort of guesses. The first is a WIMP. Now, a WIMP is a weakly interacting, massive particle. Okay, so when I say weakly interacting, this is something that does not, when it hits a sensor, let's say, like hits a light sensor or something, it doesn't detect. It's something that is out there, but we just can't detect it because it doesn't interact with stuff that we know of. Things like neutrons or stuff like that. I say neutrons. What am I doing? Sorry. Neutrinos. There we go. Neutrinos are very weakly interacting. We have billions of them passing through us all the time. But they don't interact. So maybe there's a lot more neutrino flux out there than we know of. Maybe it's something else that we just don't know about because we just can't detect it. That's what weakly interacting is talking about. The other thing that could be is a macho. Wimps and machos. NASA and astrophysicists love acronyms, by the way. Macho is a massive, astronomical, compact halo object. Okay, so these are big things. These might be things like brown dwarfs, failed stars, whatever. There's stuff that definitely has mass, big stuff, but they're just so dark we can't see them. They're just so dark we can't see them. And so, we don't really know right now what dark matter is. There's debate about, it's probably a combination of both, honestly. Could be something else. Could be something. This is one of these edges of physics we're at right here that people just don't know. So this is what dark matter is. This is how we know about dark matter. It all has to do with rotational rate of galaxies. And these are two potential solutions to what dark matter is. Let's talk about the other dark thing. Let's talk quickly about the fate of the universe. So the universe, if I draw a graph here, we're going to put R. Remember, R is the cosmic scale factor. Think of that sort of as the size of the universe. And we're going to put time here on the x-axis. Now, we are right here. Okay, so let's just say we are right here on this graph. At this moment in time, the universe is a certain size, and it is this current time. The question is, how has the size of the universe changed over time? Okay, there's a couple thoughts on this. So there's a couple ideas, and a lot of it has to do with the density of the universe. Now remember, density is mass over volume. The more mass a certain volume of space has, the higher density it would have. And the higher density space would have, the higher the gravitational pull. So let's start. Let's say, for instance, we have a very high density. Let's say, for instance, we start down here. We know Big Bang. We expanded very quickly. Whoops, draw a straight line. But that expansion slowed down, and let's say eventually the size of the universe is going to basically even out. The expansion of the universe is going to sort of cancel out with the gravity, and they're going to come to a compromise, and the universe is going to get to a certain size, and it's going to stop right there. This is where the density of the universe would equal rho c. And this is what we call the critical density. This is the density at which the universe would just stop its expansion. It would get to a certain size, and it would just sort of stop. Now, we have an equation for critical density. I'm not going to derive it. Again, this is another thing that you can look at in review, but we have derived it before, but I'm not doing that over Zoom. Thank you. Let me write that down. We're using the proper exponent. 3 over h squared, h is Planck's constant, very important term, over 8 pi g. So you can calculate the critical density. It's done mathematically based on gravity and a bunch of other things, and you can calculate it from the data booklet. We know all these things. So if the density of the universe is equal to the critical density, we'd say things are pretty flat. Let's say our density is higher. The actual density is higher than the critical density. Well, we still have the Big Bang. We're still going to be going through a time like right now, but because there's going to be so much gravity pulling everything back in. Oh, I don't want a straight line. Because there's so much gravity pulling everything straight back in, the universe is going to sort of collapse back on itself, where rho is greater than the critical density. We call this a closed universe. And by the way, this was a flat universe. So the closed universe is where, well, the universe expands, but then at a certain point, there's so much density, the gravity takes over, and it's eventually going to start pulling everything back in, and then everything's going to squish together. Maybe then it'll make a new Big Bang. Who knows? Then another idea is, well, the universe is not very dense, and it's just going to keep increasing. It'll slow down, because gravity is obviously going to slow things down, but it's never going to reach a flat slope. It's going to always be increasing in size. This is called an open universe, and this is where your density is less than the critical density. There just isn't enough mass to keep gravity from overtaking the expansion. It's going to always be increasing. The rate of increase will be less and less, but it's just going to keep increasing. And scientists for many years debated about which one it is. A lot of scientists believed our density based on observations, based on looking at what's out there and what we know about space. They believed we were right here, that rho equals rho c. Thing that we're equal to the critical density and all that. So they did a big experiment a few years ago. When I say a few years, like not more than like 10 years ago, less than 10 years probably. They did an experiment where they measured very distant stuff. They measured the recession velocity of very, very distant stuff, and they tried to measure it very, very accurately. And they wanted to figure out what is the rate at which expansion is slowing down. What is the rate at which the expansion is slowing down and things are, because gravity is attractive, so expansion has to be slowing down. And when they did this experiment, they got a negative answer. They got an answer that is something like this. We had the Big Bang, and it got flatter, but right now we see that the acceleration is actually increasing. The expansion is actually increasing in rate. The universe, what we believe now, is the universe is actually increasing its expansion. This is the current thought. Now, this is a big problem, because scientists are trying to think, like, okay, well, we know gravity is out here, but what other force would cause the rate of expansion to get faster? None of the forces we know about would do that. Okay, strong, weak nuclear force, those just happen in the nucleus of the atom. Electromagnetism really doesn't do anything to stars and galaxies. Gravity is attractive. Those are the four forces we know about. That's it. What scientists decided, and certainly this is not a closed debate, but scientists believe that in all matter, in all energy, all around us, there is some energy, there is something out there that is causing the expansion of the universe to increase. We don't know what that is. Not a clue. We call this dark energy. Dark energy is usually used by sci-fi authors as an evil sort of thing that is going to corrupt the universe. No, it's just dark because we don't know what it is. We think it's a property of all matter, all energy, all everything. But we just don't really know what it is. There's some ideas. People have ideas, but again, this is an open area of physics. And so this is one of the reasons I really love astrophysics, because this is not something that people know really well. In fact, these measurements and all, there's a lot of uncertainty behind all this. I saw an article a few weeks ago that people were saying that, well, this didn't really happen. This isn't true. The results were incorrect, and things were more like this. We don't know. And so as you go out into college and beyond and get jobs, some of you might start solving some of these questions. Some of you might start figuring this stuff out. The people that figured all of this stuff out, they were once in your shoes. They were once little high school juniors that thought they sort of knew something, but they probably thought they knew more than they really do, but they're still trying to figure things out, okay? You can be one of these people that figures this dark energy, dark matter out. And maybe when we find out about dark energy, maybe we're going to find it's something we can use. Maybe it's something that we could actually tap into on Earth to provide energy in a more useful form, like electricity or whatever. It's exciting things. So this is further cosmology. This is just looking at some of the current issues. I think some pretty interesting things. Looking at the universe as a whole. How it's expanding, what's going on, what we do, and what we don't know. That's an important part of science. Don't forget that there's a lot we don't know. A scientist, if you ever find a scientist or somebody that says they know everything, they're a fool. That's somebody to not pay attention to. The whole point of science is to be able to figure out things that you don't understand. And that's something I hope you're going to keep doing next year with your new teacher and really foster a spirit of creativity. For this week, I have a cognitive assignment. I believe it's a reading assignment. Just read over some of the stuff. And then we're going to have a Zoom session. I believe our Wednesday Zoom session is going to be a little bit delayed because we have junior locker clean out and all that kind of stuff. So I'll push it back to 2. But I really hope all of you will tune in. I'd really like to just celebrate with you. We'll talk about cosmology. We'll also do a reminiscing on the year and sort of talk about what's been going on and look forward to the future, because all of us have some exciting things coming up in the future. So really hope I can see all of you there, sort of a last class kind of thing. And so it's been Mr. Reynolds. This is Further Cosmology. I'll catch you later.